Just like we have regular quantities and angular quantities, things like forces and torques, so too can we have angular momentum. Now, angular momentum here uses the symbol L, but it behaves very, very similar to the normal or tangential momentum that we just talked about, or linear momentum that we just talked about. The idea behind angular momentum is it deals with systems of rotations, and just like with our normal momentum, it is conserved if there are no external torques present of the system. So it's very, very similar to the momentum that we just dealt with. So if there's nobody coming in from the outside and pushing your system so that it spins around, your angular momentum is going to be conserved. And this angular momentum is important not only for physical, like people's rotating around, it's also relatively important for things like photosynthesis. One thing that we'll discuss a little later on and gets discussed quite a bit when you're dealing with different areas of physics is conservation of angular momentum actually explains why different atomic states get populated by excitations involving light. In other words, light by itself, like a beam of light, has an intrinsic angular momentum, and it's only through angular momentum conservation, typically speaking, that those beams of light can be observed. Now, we're going to look at a physical example here, mostly because I don't talk about light much in this particular course. But the idea is, let's say we have a figure skater here. Figure skater starts off with his arms extended, giving him a large moment of inertia because r is relatively big, and this figure skater rotates with a angular velocity of 2 hertz clockwise. What this person then does is they pull their arms in. Pulling their arms in actually decreases r in the moment of inertia, and thus decreases the value of I to a smaller value. So what you might want to figure out here is what's his new angular velocity when he pulls his arms in. Now, if you've ever watched anybody figure skate, maybe this is a Canadian thing more so than a US thing, but I've watched a fair bit of it. When a figure skater pulls their arms in, they actually rotate faster, right? And they use that to, I don't know, do like figure skating stuff. This is actually a direct application of this conservation of angular momentum. Because when you pull your arms in, there's nobody outside of you spinning you around. It's you who's doing the thing, and you're internal to the system. So just like before, what we want to do is we want to look at a case before and after. So we want to look at this before he pulls his arms in, and after he pulls his arms in. In this particular instance, this person is the only thing present. So there's only going to be one momentum we need to look at. So in the before case, we can calculate the angular momentum by simply taking the moment of inertia and multiplying it by the angular velocity. So here, to find my moment of inertia, which uses L, yes, this is an L, it's kind of hard because it's lowercase, what we're going to do is we're going to take I, I'm going to use capital L here just so it's clear what we're dealing with, and we're going to multiply this by the angular velocity. Here we actually have both of these things. Keep in mind the angular velocity is a vector. So here our moment of inertia is 100 kilograms meters squared. So we have this quantity, and we're going to multiply it by our angular velocity. Now, in order to be consistent here, we are going clockwise, so I'm going to indicate that direction with a minus sign. And our angular velocity is 2 hertz. So putting this all together, you can combine the units however you like. I'm just going to leave them. We have negative 200 kilograms meters squared, and we might as well just leave this in hertz. You can convert hertz to 1 over seconds if you choose. So there we go. And that's our total angular momentum because we only have one type present. Likewise, given that there's no external torques, this total angular momentum should remain the same. If we have an external torque, it can change, but in that case, there's actually no point in using angular momentum as a tool. If you do have a net torque, you might as well calculate an angular acceleration because you're going to have to deal with it anyways. Now, with this being said, afterwards, this angular momentum is still equal to I times omega. The only difference is these are going to be different quantities. So let's change their color here to red. Now, in the after case, you've been told that your moment of inertia has changed. It's changed from 100. It's changed from 100 to 75. So here, our I is going to be 75 kilograms meters squared. And omega here is what we're trying to find. Now, we can solve this relatively quickly because I know that 75 kilogram meters squared multiplied by omega must equal to negative 200. So here we can cancel out some units. On this side we'll have 200 hertz. I've canceled out the kilograms and meters squared on both sides, and here we're going to have 75 times our new omega. With this, you can solve for omega. So first of all, the direction is still going to be negative. That's not going to change. And if you take 200 and divide it by 75, you'll get 2.67 hertz. And what you'll notice here is, just like if you were to go and watch figure skating, the omega has actually increased if you compare his new one to his original one. They're both in the same direction, but one is faster than the other. And that's what you'll see. Literally, if you spin yourself around in a circle, get yourself a nice constant velocity or constant angular velocity going, and you pull your arms in real quick, you'll spin slightly faster. And that's because there's no external torques acting on you, ideally speaking. Of course, there can be things like friction with the ground, your muscles actually straining as they twist, that can create a type of external torque, but in this instance, figure skating is a good example because there's not too much friction between you and the ice.